everyone doing today? Hope restful weekends were had. Anyone need anything before we get started? Okay. So, minor reminders. Today's the 17th. We have normal lab again starting this week until otherwise indicated. And I kept forgetting this until recently. I don't think there's class on Friday. As a result, we obviously won't have lecture that day. It doesn't interfere with our lab schedule this week though, so do still come to lab as normal. And I've had to rearrange what I said we were going to do to make sure that I can squeeze everything that we need to talk about in this week. Today, we are going to both look at the slide question that I kept saying we would do, and also talk about elastic potential energy to make sure that you've seen it before lab this week. Wednesday this week, we'll continue looking at examples involving everything we've already talked about and introduce the formula for power. It's a very short formula. And then homework is still currently scheduled to be due Monday the 24th at midnight. Since it's midnight, we'll have the class lecture itself to talk about the homework and answer questions and put the problems together. And then next week we'll do chapter 6. That's currently the track that we're on. I'll lose my train of thought mid-sentence as I usually do after Monday. I'll revise if anything ends up taking longer than I expected, but that's our current schedule. And as I said, today we're going to look at at least one sample question, and by the end of things, make sure that you've got the formulas for elastic potential energy in your notes. Any questions about any of that before we get started? All right, so we've discussed friction in this class, the formula for how to calculate it, where it comes from, mostly in terms of just force so far. But all force is technically capable of doing work. And so it's important to discuss how friction affects work and energy levels. If you're in a car's moving forwards, and since it's moving, it must have some amount of kinetic energy. What effect do you think that the friction between the car and the road is going to have on the car's energy levels? Say again, sorry? Correct. The car has to work against friction. Friction is going to be taking energy away from the car, and the car has to keep doing more work to make up for that energy loss. Friction, and the work that friction does, always exists to take energy out of mechanical forms. The kinetic energy that makes a car move forward, that is a mechanical form of energy. All the forms of energy we've talked about so far have been mechanical, and that's, for the most part, going to remain true for 1500. Friction takes mechanical energy out of a system and converts it into non-mechanical forms. All forms of mechanical energy have something to do with movement or possible movement that we, on our human size scale, can observe and measure. Whereas non-mechanical forms of energy either don't involve motion at all or involve motion on the subatomic level that we can't readily detect and identify. Friction, back up. let's say this could be the car, this could be pushing a box along the ground. Some force is exerted forwards on some object, and the object moves some distance forwards. The formula for work equals force times displacement, tells us that you'll be doing work on this object as it's being pushed forwards. The only prerequisite is that the force must be parallel to the displacement. So if you push forward on a box and the box moves forward, you're doing work, you are giving energy to the box. The box's energy total rises as a result of your efforts. What direction does friction point in between the box and the floor in this case? Very good. It always just opposes the direction of motion. And interestingly, even though it's in the opposite direction as the original force and the displacement, it's still parallel. It's still in the same axis, which means you can plug the force of friction into here with the forwards displacement to figure out the amount of work that friction is doing on the box. And that amount of work is the energy friction takes away from the box. Technically speaking, if force forward is positive and delta x is positive, the friction backwards would be a negative number, points in the opposite direction. That negative would make the work done by the friction a negative number. That negative represents the fact that friction takes energy away from things. Every time you take your two hands and just rub them across each other to warm them up on a cold day, the friction between your palms takes kinetic energy away from your hands and turns it into thermal energy in your skin. It takes it and turns it into a non-mechanical form, and that tends to be thermal energy. This is why after you hit the brakes in your car, if you go and examine the tire tracks that you just left on the road, they tend to be warmer than the road is by itself, because the friction between your tires and the road turn the car's kinetic energy into thermal energy in the ground. So friction can do work. It specifically takes energy away from things and turns it into a non-mechanical form. This still follows the law of conservation of energy. That is still technically true, because the energy friction takes away still exists, it's just not mechanical anymore. Yes?
And the formula for work, is that the parallel friction, right?
Yes,
Okay.
this is the parallel symbol. Force and the displacement must be within the same axis, even if one of them points backwards. So, no matter how much energy friction takes away, the law of conservation of energy is still technically correct, because if you lose 1,000,000 joules of kinetic energy and it all becomes thermal energy, the energy still exists, so the totals from start to finish are still the same, but they're in different forms. And you can't really use the thermal energy to power anything anymore, because now it's just making all of your equipment hot. So this equation that we've been utilizing, the law of conservation of energy, is still true. But there's a slightly different form that might be more helpful for what we do specifically in this class. Since in this class we're going to talk mostly about mechanical forms of energy. So this version here that I'm going to start using with you today is a derivation of the original law of conservation of energy. It refers to the same thing, it's just kind of a more specialized version. This says the total amount of mechanical energy in a system before some action occurs is equal to the total amount of mechanical energy in that system after that action occurs, plus however much work friction took away from the system, the magnitude of the work not conserved. This still follows the law of conservation of energy. The totals of all energy on either side are still the same. This just allows us to specify how much energy friction took away that is no longer in a mechanical form.
What does NC stand for?
Not conserved. WNC is work not conserved, which friction, the work done by friction is defined as work not conserved. And we don't call it not conserved because it destroys energy. We just call it not conserved because it doesn't conserve mechanical energy. So, broadly speaking, energy is still conserved, the energy still exists, but friction doesn't conserve mechanical energy. So that's why it's referred to as work not conserved in most textbooks. Questions about this as a concept so far? Okay. Utilizing this, I'd like to take a look at this slide question that I hinted at the past couple of days. We're going to quickly look at what is involved in this process, both without friction, and then show how friction is factored in. So, at the top of this slide, you are 5 meters in the air. What form of energy would you have in that position if you were sitting on the top of the slide? Well, you would have energy. Kinetic energy would be 0 because you're not moving yet. But what form would you have sitting 5 meters in the air? GPE. Very good. So, mechanical energy initial, if we consider the initial state to be just sitting on top of the slide before you begin using the slide, in that state, you'd have some amount of GPE, but no KE, because you're not moving yet. So I'll go ahead and fill in GPE initial as the sum of our initial mechanical energy. This is all the energy we have before we start moving. Now after you start sliding down the slide, what's going to happen to that GPE total? It's going to decrease. As you go down the slide, your height compared to the ground goes down. As your height decreases, your GPE will also decrease. Now, energy can't be created or destroyed. It has to go somewhere. So what form would it turn into as you're sliding down the slide? As your height decreases, what increases? Yes, and I think you were mouthing that earlier, because my ears aren't great. So much like the inverse of throwing something into the air, as you descend, GPE drops as your height decreases, but your velocity will rise on the way down. That's kind of the point of the slide. You want to go faster on the way down because fun. And in a vain attempt to quantify fun, more fast is more fun. So the higher you start up, the more energy converts into KE, and the greater speed you should be moving at the bottom. This is true whether you are falling or not. In the case of just dropping something from 5 meters in the air, the GPE would convert directly into KE very quickly. However, you'd be moving straight down and you'd go splat. The purpose of the slide is to redirect your final velocity so that you eject from the slide sideways rather than straight down into the dirt. But even if you're not falling, it's still a direct conversion of GPE into KE as height decreases and velocity increases. So, Ignoring everything else for a moment, as you approach the bottom of the slide and your GPE drops to 0, your energy will turn into KE and you'll eject from the slide at a certain maximum velocity. And if the slide were to end at the height of the ground, that would be the end of it. If the slide ends, you're now on the ground. If you're at a height of 0, at that point, your GPE would be at a minimum. If your height is 0, your GPE is 0. And all of that initial GPE will have had to turn into KE. So, if you were only looking at what is your top speed at the lowest point of the slide, this is your math. This represents all the energy from start to finish in that case. As long as you know the mass of the child and the starting height of the slide, you can solve for final velocity and figure out how the fastest speed you are going on this particular device. Questions getting to this point thus far? Okay. Now, does this particular slide end at that height? No, this particular one continues going and rises back up slightly so that rather than launching straight sideways and possibly rolling into the dirt, you launch upwards and eventually into a pool of water, which also sounds more fun. Now, this was the lowest point. This is the spot where GPE is 0 and KE is max. What happens to those two forms of energy as you raise back upwards slightly?
They switch out, like, after GPE leaves.
Correct. You'll lose some of that KE as it turns back into GPE. Not all of it, because you're only rising 1 meter compared to 5, but some of it. This does. So if we consider the end of the slide, rather than the very end, the part that's elevated, to be the final point, rather than that lowest spot, you'd gain a little bit of GPE back, but that comes at the expense of KE. Because the initial total is the same, it's just now that total is spread across two forms instead of just one. So in order to do this, to have that launch into the air, you do launch more slowly. You're just gaining the benefit of launching upwards instead of sideways. So that comes at the expense of some of your speed. That's another term on the right that's taking up some of the energy. That means that less of it is KE, and that's going to drive your final velocity down. You guys see how that math would play out? I believe from previous times I've calculated this. That if we ignore friction to get to this final speed, it would come out to be about 8.86 meters per second, which is pretty quick. It's a good slide. But getting there, thus far, we have ignored friction. We've treated friction as if it doesn't exist. Any questions about any of what's on the board getting up to this point, where we've analyzed the launch speed at the 1 meter raised up end of the slide without having factored friction in yet. Okay? Now, a frictionless world is all well and good until you need to stop. But friction does exist. And because friction does negative, non-conserved work, it takes energy away. Once we factor friction in, that's going to be something that slows down what's happening here on the slide. Again, I re-described the law of conservation of energy into this form. Total mechanical energy initial equals total mechanical energy final plus the work not conserved. Up till now, if we haven't been considering that friction exists, the work not conserved would be zero. If there's no friction, it's not doing any non-conservative work. Once we start counting friction in, though, this term stops being zero. We have to put something in there to account for how much energy friction is taking away. And to do that, under normal circumstances, you may use the formula for work. You can calculate the work that friction is doing with the force of friction and the displacement that force is applied over. And so you could simply plug in the work formula for that term, and that would be a way of counting how friction is involved. Now this particular question is a little bit odd because it didn't tell us what friction is doing in the traditional way. Instead, it tells us that the work done by friction is 5% of the initial potential energy. Which, it's still telling us the amount of work friction does, it's just doing it in kind of an atypical way. I like the way it's describing it here, but it does take a second to kind of process how you would factor that into your math. In this specific case, we don't need to use the work formula to find the work that friction does, because we've been told the work that friction does is 5% of the initial potential energy. So in this specific question, this is not a general rule, this is one of the quirks of this problem. Instead of the work formula for the work done by friction, we can write 5% of that initial energy total. Again, this is unique to this question. Other questions will give you the information in different ways. We'll have to apply it differently. But this is how we can apply the information that's given to us here. I do think some technical settings do describe friction in this way in terms of the percentage of energy it takes away. So this is applicable to some disciplines, the way it's written here. When we factor in friction in this way, that's going to be another place that energy gets drained into, some of it at least. Which means there's, once again, going to be less energy becoming kinetic, which is going to drive down that launch speed again. And so this final version of this equation would tell us the launch velocity off of that 1 meter raised up part of this slide after we factor in friction. So this final version includes the the 1 meter elevation on the end, and that friction exists. My goal was to kind of piecemeal through slight variations of this one to show how they're connected, to show how adding on each piece changes the original version. Does that approach, has that felt beneficial? Okay, mostly nodding. Let's see. For this specific example, by this point in the algebra, VF is still the only unknown, so we can solve for it. To do so, I'm going to send everything that isn't the KE term over to the right. So the GPE initial term, 30 times 9.8 times 5 meters, minus the amount of GPE we regain at the end, rising to 1 meter in the air, minus the amount of our total energy that we lose to friction, will then finally equal the amount of energy that successfully becomes and remains KE by the end of the slide. Notice, after putting it into this form, the left side does show this is our total energy, and these are the things that take energy out of that total, giving us a certain amount left that successfully becomes KE. If we were ignoring friction, this piece wouldn't be here, there'd be more energy left to become KE. If we didn't have that 1 meter raise on the end of the slide, this term wouldn't be here, that would be more energy in the form of KE. With all these variables here though, I believe this entire left side boils down to 1,102.5. Left side can simplify to 15 times VF squared. And that should make our final velocity, launching off of this 1 meter raise and after counting friction, as 8.57 meters per second. Which is not a very big loss. Without friction, it's about 8.86. So we only really lost like 0.3 meters per second. It's not a big deal. On the human scale, factoring in friction becomes more important when you're looking at high energy machines for the most part, because like 5% energy loss becomes a bigger deal if you're dealing with like a 10 million joule turbine. And suddenly all that energy is becoming friction, which heats up the turbine and eventually melts it. So counting in the friction becomes very important depending on what sort of job you're doing with it. And most of the time it's small enough that we can almost ignore it, but it's important to know how to factor it in. Any questions thus far about any part of this progressively longer example? All right. The next thing, actually the last thing that I want to do today is talk about EPE. So we're going to be switching gears a little bit. Does anyone need anything before we switch off of this and on to something else? All right. We We will do more examples that involve friction, just to help you get your footing with it. I just think it's important to talk about this right now before it comes up in lab, possibly this afternoon or tomorrow morning. We're going to add a new form of mechanical energy to the list that we currently use. Both kinetic and GPE count as forms of mechanical energy because they do involve motion somehow, either active motion or motion that could happen. Elastic potential energy is very similar in that it is also about motion that could happen and will happen once you release the system. Like GPE, this is a form of potential energy, so it's stored energy. It's energy that is going to be used later. Specifically, hence the name, it is energy that is stored in the deformation of an elastic object. To start defining the physics words in that sentence, in terms of physics, the physics definition of elastic objects and elasticity is an object's ability to deform, to change shape, and then of its own power go back to normal. Something is elastic if it stretches and then can unstretch by itself. Springs are a good example. As long as I don't pull this hard enough to break it, I pull it and, oh, why did I do that? It will return to its normal size. That is the definition of an elastic object. And elasticity includes things that compress as well as stretch outwards. Balls, bouncy balls, and all sports equipment are included among this list. When you throw a basketball on the floor, or really any turbo bouncy ball that you get out of those machines at the grocery store, at least I used to, in the moment it hits the floor, it technically changes shape. You can't really track it with the human eye super well, but it does squash on impact before going back to normal. That is also deformation, and it is also able to, under its own power, return to its normal size. That's what makes an object elastic. And the definition of deformation is just, it changes size from its original in some way, and if it's elastic, it then goes back to normal. Really, any object can deform, because you can take a hammer and hit a rock and break it into pieces. That's technically a deformation, but rocks aren't elastic, so they don't go back to normal. That change is permanent. It is only elastic objects that can return to their original shape that store EPE inside of them. When you stretch an elastic object, energy is stored in that stretch, which is then released upon it returning to its original shape. This is why all spring-loaded and rubber band-loaded slingshots work. By stretching on this particular spring, I am storing energy inside of it that is, I'm not going to do it because I don't want to hurt my fingers, but when I let go, that energy is released, it becomes KE in the object that is now being fired out of the slingshot. It's true of rubber bands, and it is again true of bouncy balls striking something and then bouncing back. In the moment this basketball hits the floor, it compresses, and in that compression, all the KE it had a second ago, because it was moving before hitting the floor, all that KE turns into EPE, and it's stored in the moment that it's compressed like this. At that moment of maximum compression, it doesn't have any KE anymore, because it's not moving for the split second it's stuck on the floor. And then once it goes back to its original shape, it literally springs off of the floor, and all of that stored EPE becomes KE again. And that's why it bounces back upwards. Objects that aren't elastic don't bounce back upwards. They don't store the energy to release again. They just lose it upon hitting the floor. Because this doesn't stretch. Questions so far? Okay. So all elastic objects can house EPE inside of them. The formula for EPE, labeled down here, is 1/2 times k, which I will define in a minute, times x squared. This x term is the magnitude of deformation. It's by how much the object has been stretched or compressed. This tells us that the longer you stretch something, or alternatively, the more you compress something, the more energy is stored inside of it until it goes back to normal. This is why the further back you pull on a rubber band slingshot, the faster it fires. You store more energy in it, and then the projectile gains more energy as a result. This was also true of the marble cannons that we used in the first 2 weeks of lab for this class. If you'll remember, to use the cannon, you would have to push into its mechanism with that stick, and in doing so, you were compressing a spring inside of the cannon. The more settings you tick back, the further you were compressing the spring inwards. Therefore, it had more energy and could shoot at a higher speed. So that x term is the amount of deformation. And it's important to note the number you plug in there needs to be specifically the magnitude of the stretch, not the final length. Let's say hypothetically, this spring begins at 1 meter long. Let's just say its base state is 1 meter. And then I stretch it to make it 3 meters long. What is the magnitude of its deformation? How much longer is it than it's starting? 2. It was 1, now it's 3, so it's 2 meters longer. That means that 2 is the number that goes in here, not 3, not 1. So it's specifically the change in size, not the final size. Additionally, example, if I put some numbers to the basketball, if it starts with a 50 centimeter diameter and squashes to 20, what value do you put in the formula? It became 30 centimeters smaller. That's the amount of compression. That's the magnitude of deformation. Yes?
For the units for this one, are we still having to convert to meters?
Yes.
Okay.
The reason for that is because of the K value. And this is a new constant. It's a new one where every object is a different one, and so you don't have to memorize them. K is an object's spring constant. This is a measurement of how elastic a specific object is. If you've interacted with many rubber bands or springs or hair ties, you probably noticed some of them are more elastic than others. Some of them are harder to stretch. Some of them take more force to make them actually elongate. Or some of them stretch really easily. The K, the spring constant, is the numerical measurement of that. What spring constant is, it is a measurement of how much force it takes to make something stretch by a certain amount. Say, for example, I was trying to find the spring constant of this spring, and I exert 1 meter on it, I exert 1 Newton of force on it to make it 1 meter longer. 1 Newton over 1 meter would be a spring constant of 1 Newton per meter. It takes 1 Newton to stretch it every 1 meter. So if I pulled on it with 2 newtons of force, it would become 2 meters longer. Conversely, if I took a different, much tougher spring, and it took 10 newtons of force to also stretch by 1 meter, 10 over 1 would be 10 newtons per meter. It takes 10 newtons to stretch every 1 meter. And that drives up the spring constant. That also drives up EPE. The more rigid a spring is, the higher its spring constant, the more energy it can store for the same amount of stretch. Conversely, though, it also makes it tougher to deal with, because the higher the spring constant, the harder you physically have to pull on a spring to actually, make it do anything. Excuse me. Likewise, you can rearrange this formula into this form. Fs is spring force. A spring will exert a force back on you when you pull outwards on it. So if I pull 10 newtons outward on this spring, it pulls 10 newtons inward on both sides, like tension in a rope. And that force increases the longer I stretch it, because it takes more force from me to stretch it out. This is just Newton's third law again. The force I exert on it, it exerts back. Questions? All right. That's actually everything I wanted to cover today, and I don't know if we have enough time to go into a full-length example. So we can conclude the lecture here. Do bring all your notes from today to lab, whatever day you have that, both the EPE part, but also the previous example as well. And Wednesday, we will look at more examples and also define power. Close out chapter 5. Anyone need anything right now? All right. Have a wonderful day, and I'll see you for lab or lecture Wednesday.